To get the derivatives for the trigonometric functions, all I really need to do is find the derivatives for sine and cosine, because the rest of them can be broken down into sine and cosines, so I can just use the quotient rule. Now it doesn't matter if I begin with sine or cosine, because they will both run into the exact same limit problem. So I'm going to do sine because it's my favorite function out of all of those ones. So I'm going to set up a standard limit problem. No need to write f of x. Sometimes there's a serious disconnect between my brain and all of the other parts of my body. So I'm just going to change that. I think it's a plus, I'm pretty sure. I'll find out after I've done all the work. No, I definitely know it's that. And it's still a limit, obviously, so now I'm going to factor out the sine x and the cosine x, because as h approaches 0, it's not going to affect it. So we'll do this, just to make it nice and easy what we're looking at. So I already evaluated the limit for cosine x as h goes to infinity and sine x, because it doesn't change. H isn't in there. And this is the problem I'm going to run into with cosine as well. I'm going to get a cosine h minus 1 over h and a sine h over h. And I can use just a numerical method by just putting in varying numbers very, very close to 0, and I'll see what the limit is, but that doesn't really cut it for like proofs and stuff like that. It's technically a guess. So how to go about doing this? Well, what people did was use, I think there are more than one way of going about it, but the way I learned was to use the geometric method. And in fact, you can really just look at whoa, where'd it go? Oh, there it is. You can just look at this and tell what's going on. I mean, normally you can just have a look at it. Well, let's just explain what's going on. So what's going on here is I've got the sector of a circle, and that sector is BA. What the idea is to use the limits. Well, first, what is generally done is, it's nothing really that complicated, but this is what they do. They change h to theta. So it doesn't really matter what it is. Theta is in radians. So here's theta when it goes to 0. And what we do is we look for a situation where we can get this kind of information out of it. And then we use the squeeze theorem. Now, since this sector of a circle is in radians and the radius is 1, then this length is equal to theta. So the arc length of BA is equal to theta. So I've already got my theta in here. And what I'm really looking for is ways I can get a sine theta somehow, basically. And to use the squeeze theorem, so I'm going to use this triangle right here and then this big triangle as well. So imagine, just forget all this crap in the middle. Imagine I've got these two lines and this line right here. What happens when theta goes to 0? Well, I mean, this line straightens out, and if I were to think of it as just very, very small, they're almost the same height, and they're eventually going to approach the same value. So what we can do is just use the squeeze theorem. So this line is ahead of this line, which is ahead of this line. So these two lines sandwich this line. So when theta goes to 0, this line is going to start going this way, and until it gets to right there, this one's going to just basically stay where it is, and this thing will straighten out. There are a lot of different ways you can think about it. You can think about it in terms of area. It's just whatever you feel like thinking about. So without further ado, I'm gonna try to extract. Oh, I didn't mean to do that. I'm gonna be trying to extract sine out of this. So, as I said, I'm looking for something smaller than this and something larger than this, so I can use the squeeze theorem on it as it goes to a. So the first way I'm going to try to get sine theta is to use this angle right here and do an opposite over hypotenuse. And here the radius is r, so I want to be able to use this side as my hypotenuse for sine theta. So I'm probably going to be using this line right here. And I need to do a little bit more than that with proofs. They want to well, how do you know that this side is bigger than this side, blah, 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 whatever. So we'll go ahead and start doing that for this triangle. So I've got arc length BA, which is equal to theta. Because it's a radians, the radius is equal to 1, then it's just going to be whatever the radian measure is. So I have theta. And theta is greater than the line BA. This length theta is a curve. BA, these are all 1 point, by the way, it's just terribly drawn. BA is a straight line. The shortest point, or the shortest path between 2 points is a straight line. So this is being a straight line, has to be shorter than BA, the curve. So theta is greater than BA. Now BA is greater than BC, because this is a right angle, this is a right angle as well. And that would make this the hypotenuse. Now hypotenuse is the side that is opposite the greatest angle of a triangle, and that would make it the longest side. So BA has to be bigger than BC if it's part of this triangle. Now I can go ahead and use this angle theta. What I'm basically going to do is say the sine of theta is less than theta. How do I know that? Because BC is less than BA. And BA is then going to be divided by the hypotenuse of the triangle, and the hypotenuse of the triangle is bigger than BC, so it has to be smaller than theta. Man, why am I always sick? Damn. So I get this inequality, and I can divide out by theta. Or I could leave it like that and then just do it later, but sine theta is less than theta. Sine theta over theta is less than 1. So I've got something that's smaller than this. Now I need to work on this side right over here, this big triangle. And I'm going to do it the kind of, proofy way or whatever. So I'm going to say I've got theta, and it is going to be smaller than BE plus EA. And then the next logical step is to say that DE plus EA is greater than BE plus EA. And I can say that because this is a right angle right here. This is a tangent line. This is tangent to this circle at that point right there. So this is a 90-degree angle. And if this is a 90-degree angle, that makes DE the hypotenuse. So DE has to be greater than BE. So I can say that. Now, what I'm going to do is, instead of saying DE plus EA, I'm just going to write this as DA. So theta is less than DA. So now I can go back, now that I have this big side of this triangle, now I can go back to theta and have a look at what ratios I can get that will make sense for me to use. It doesn't make sense for me to do sine again because I don't know what the length of BD is. But I do know the length of OA. Because this is a unit circle, this is going to be the radius. So I know the adjacent side, and I need the opposite side. So I can use tangent, which is opposite over adjacent. DA is the opposite side, so tangent times the adjacent side is equal to DA. Tangent theta times, this would be OA. But since it's a unit circle, OA is just going to be equal to 1. So DA is equal to tangent theta. Theta is less than tangent theta. And tangent theta is sine over cosine. So if I multiply both sides by cosine and divide by theta, I'm going to get cosine theta is less than sine theta over theta. So now I have two inequalities. I have sine theta over theta, and it is less than 1 but greater than cosine theta. Now I'm going back to this original problem, the limit of theta going to 0. What is that when I have sine theta over theta? So I've got this again. Sine theta over theta. So, what is this limit? Well, if I take the limit of all of these, or just these two, let's say, hold on, let's think about it this way. Take the limit as theta goes to 0, cosine theta, this is equal to 1. I know that one, and I also know the limit as theta goes to 0 of 1, which is just equal to itself 1. So I basically get as the limit theta goes to 0, 1, so by the squeeze theorem, this limit has to be 1. And I can see that in this picture here. Look at this triangle as it goes over here. As this triangle goes here, they're both going to go to the same point, and this one's going to be in the middle. But they're both going to eventually approach that point A. So by the squeeze theorem, I say this limit is equal to 1. So now going back to this problem up here, I still need cosine. So I solved this one. So let me just write this over here in a different color. Sine theta over theta Now I still have this one over here to deal with. So I'm just going to write it out by itself. Limit h goes to 0. That was the hard part, by the way. This isn't hard. So what I'm going to do is multiply top and bottom by cosine h plus 1. It's so I get a cosine squared minus 1, and then I can use the sine squared plus cosine squared is equal to 1 identity, and that will help alleviate some problems. So this will be equal to minus sine squared theta. Oh, I just switched between h and theta, but it really doesn't matter. This theta, h theta doesn't make a difference. So then I'll get theta times cosine theta plus 1. And now what I'm going to do is now that I know this limit right here, I've got a sine squared and theta down here. So what I'm going to do is I'm going to pull out sine theta over theta multiplied by minus sine theta over cosine theta plus 1. And this is a limit problem, so let me continue. So let me rewrite the whole thing. So the limit theta goes to 0, sine theta over theta times minus sine theta cosine theta plus 1. So now I can take the limit. I know that this limit is 1, this limit is 0, this one is 1, and this one is 1, so I get 1 times 0 plus 1 plus 1, so the whole limit is equal to 0. So I go all the way back. Yeah, I know, right? Pretty annoying. So now I know, I'm going to write another one. The limit as theta approaches 0 of cosine theta minus 1 over theta is equal to 0. So now I go back to my original problem here. I'm going to do it in different colors. It's so messed up. So this was the original problem. I had sine x times the limit of h going to 0 of cosine h minus 1 over h, and I know this is now 0. And then I have cosine x times the limit as h goes to 0 of sine h over h, and I know that this is now 1. So that means that the limit of sine, or the derivative of sine, that's what I meant, is equal to sine x times 0, which is 0, plus cosine x times 1. So that's just equal to cosine x. And that is how you get that. So it's quite laborious, and I guess I may as well do cosine while I'm out here. I don't even know how that dot got the what. Alright, I need to move down. Alright, so I need to get cosine. Same procedure as last time. Organize like terms. So cosine x, and again I have cosine h minus 1 over h minus, what's this, sine x sine h over h, or I can write this as cosine x limit h goes to 0, cosine h minus 1 over h minus sine x sine h over, no, I forgot the limit. So you see what I mean about running into the same problem. I have again got cosine h minus 1 over h, and I have a sine h over h. But fortunately, I already solved this. I know that this goes to 1 and this goes to 0. So I'm going to get the derivative of cosine x is equal to, so this, oh, forgot to put the 0. So this is 0, then this is going to equal minus sine x times 1. And that is indeed the correct answer. And then of course the other ones I can just do the tangent. I just use the quotient rule, and I use the quotient rule for the rest of them, and I'm not going to do those. I've already spent enough time. Have fun with that.